The next topic we're going to be talking about is tree recursion. And instead of going through definitions of exactly what tree recursion is, I think the best way to show what it is to just look at an example that we're very familiar with, Fibonacci. So, previously we defined Fibonacci iteratively, and this is a very valid definition of it, but now we're going to define Fibonacci recursively. So let's think about how we can do that. Well, let's think back to what exactly the Fibonacci series is. It's just 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So this is the first 10 Fibonacci numbers. And how do we get the Fibonacci sequence? Well, it's every Fibonacci number except for the first and second is the sum of the previous two Fibonacci numbers. And the first and second number are starting points, basically. So, if I want to find the third Fibonacci number, it's the sum of the first two. If I want to find the seventh Fibonacci number, it's the sum of the fifth plus the sixth Fibonacci number. And if I want to find the 10th Fibonacci number, it's the sum of the 8th and 9th Fibonacci number. So this is how we figure out Fibonacci numbers. Hey, but this leads us to a natural recursive solution, because now we're defining Fibonacci numbers in terms of other Fibonacci numbers, and that's by definition recursion. So if I was going to ask you, hey, what's the nth Fibonacci number? How could we define this in terms of other Fibonacci numbers? And after some thought, you might have came up with this solution. Fib of n minus 2 plus fib of n minus 1. Every single Fibonacci number, in other words, the nth Fibonacci number is the sum of the n minus 2th Fibonacci number plus the n minus 1th Fibonacci number. And this is the definition of Fibonacci. If you open up a math textbook, this is what they'll show you. So again, recursion is something you've seen before, and this should make a lot of sense. Alright, but now how do we code this? Well, we have to start, so we start with our base cases. In this case, our base cases are our starting points in finding the Fibonacci numbers. What do we need to start? We need two numbers, right? So what's our first number? Well, if they ask for the first Fibonacci number, it's going to have to be the case that it's 0. Our first Fibonacci number is 0. And these are given to us. This is how you start the Fibonacci series. So in this case, our starting points are our base cases. And then the second Fibonacci number is 1. And then, once we have that, once we have our first two Fibonacci numbers, we can build the entire Fibonacci sequence. And that is based on just returning the fib n minus 2 plus fib n minus 1. And so that gives us our very simple recursive solution to this problem. So let's just test this. So fib iter of 10, remember, this should give us 34. And so now I'm going to define, see what fib of 10 is. It also gives us 34. Now if we call fib of iter on 20, we'll get this number, and of course this should also give us the same result. And now I want to point you to something a little interesting. If we call fib iter on 30, we get this pretty quickly. But now if we call this on 30, suddenly it takes some time. What could this be? What if we call it on 32? We get another large number. What happens if we recursively call it on 32? Oh wow, it's taking some time. It'll eventually get the answer, but it's taking quite a bit of time. It took about 5 seconds. So, one thing you can immediately say, hey, it looks like the recursive version of this is slower than the iterative version. And this is our second run in with efficiency. So here we just visually could tell, based on the amount of time, that the fib iter version was more efficient than the recursive version. And the reasons why are something that we'll be talking about much more later. But just so I can introduce you to some ideas and give you some thoughts, some food for thought basically. The reason Fibonacci of n defined this way is so slow is that this is an exponential time function. And the thing about exponential time is it's incredibly inefficient. Even the most powerful computers in the world bow down to exponential time. That's how bad exponential time is. So exponential time is terrible. So, and if I gave it some large number like fib of 100, it would probably take like, I don't know, almost an entire day to figure out the result. But again, the reason this is exponential is something I'll be talking about much later in this course. So don't worry, we'll talk about this much more. And by the way, I do want to note that this doesn't mean that recursion is worse than iteration. For those of you who are still doubting recursion, there is a recursive way to define this that makes it just as efficient as fib iter. So we will also be talking about that. So let's look at how this exactly works though. So this is the reason we call this tree recursion is because it gives a natural tree-like shape of the recursive calls. So this is an example of evaluating Fibonacci. So this is a pretty large tree. And again, this is why the tree recursion solution to Fibonacci is pretty inefficient, because we're only calculating the 9th Fibonacci number and the tree is already this big. Once you get to like the 30th or 40th Fibonacci number, the tree is enormous. So that's why there has to be an enormous amount of computation that has to be done to figure out larger Fibonacci numbers using the tree recursion method. And again, we'll find a more efficient way to do this later. But basically, let's look at a small version just so you understand exactly what's going on. When I call fib of 5, it should return 3 because that's the 5th Fibonacci number. So what I do is when I call fib of 5, I'm really calling also fib of 3 and fib of 4, because fib of 3 plus fib of 4 is fib of 5. And then when I call fib of 3, I'm calling fib of 1 plus fib of 2. So here the left branch is always going to end up being the n minus 2 call, and the right branch is going to be fib of n minus 1. And so this leads to a natural tree shape. And once we get to our base cases, we actually get a return statement. And I'm not going to build myself back up the tree. You guys should be pretty comfortable with that by now. But basically, when we add this all together, we get 3. That's how tree recursion works.